Of this question, over here we have a number. To get to that number, only two operations we can do. Either copy the number 1, and initially we have 1. From this we need to go to n, which is given in the question. To go to n, we have only two operations. Either we can double it, in the sense I can just copy this 1 and then paste it, making it 2, or I can just paste it. Pasting it would become 1. So this is for any other number other than 1, because in the starting when we have 1, the only thing, if the n is greater than 1, only thing we can do to reach that n is copy. First operation has to be copy. This we need to keep in mind, because before copying we cannot get any number greater than 1, right? So that is the question. Now we can notice that if there are only two ways to go about it till n, and we want the minimum number of operations, but we want to explore all the possibilities, in the sense from 1 we have that copy is 1, and then 1 plus of this if we take as the recurrence relation. In the sense we are saying that first operation is a copy, and then give me from 1 comma 1 to go till n, right? How many operations do I need? So it will be that. Now this will in turn give me 1 plus the number of operations, 2 plus the number of operations 2 comma 1, because over here this denotes that we are doing just a paste operation. This denotes that we are doing a copy plus paste operation. So if we are copying one, we had 1, we'll be copying 1 and then pasting 1. So this amounts for 2 operations, which is this. Then if we are just copying it, we will be just pasting it, and then this pasting will amount to this. So in the next iteration of our recurrence relation, we will be passing down the size as well as the previous copy whatever was present. In the previous copy here it is 1, in the other one it can be non-1 also, like it can be greater, because over here if we see it is 1, but if we go on to the next one, here we can see that it is 2, because over here we are copying this. So the previous copy whatever was there, this is like copy paste operation, this is a paste operation, this is a paste operation, this is a copy paste operation. So in the copy paste operation we are copying 2, so now the copy will become 2, whereas the number will become 4. Now in this also we have a base case. The base case is that there are basically two base cases. One, when the n over here, as we can see 4, but our target was only 3. If our current size is greater than our target, then we can just return a number which is like int max or something, or else over here in this case 1000 will do. Next, the second thing is like if size is equal to n, then we can say that this is a possible answer, so we can just return 0 from here. Because remember, every time we are going inside, right, we are going the functional way, in the sense we are doing operations plus get me how much to go from x to x. So we are doing that. We are not passing this variable into the function and then so that we'll have to return that moves over here or else update that. We just need to return 0, that if from size to n, if they both are equal, I just need 0 operations to go from size to n, right? Similarly, we can see the logic over here. Here there is a DP array. Another thing to note is that we can just declare these two variables as global variables, so that we don't need to pass it. Global variables very important. I need to remember this, I need to remember this, so that I can just set it in the global variable and then use that global variable only everywhere instead of passing by reference also. Now these things are these are the two base cases. This is the DP check. These two are our recurrence relation. This is our post processing of the recurrence relation. The same thing from the tree we can see, right? The main motto over here was to discuss the logic and observation. In the logic and observation, we can see that to make this number k, suppose to reach that number k from 1, all we can do is CP, CPP, again CPP, something like this. And we want to make sure, suppose this is like G1 operations, this is like G2 operations, and this is like G3 operations. So my answer would be G1 plus G2 plus G3 operations. Now I need to minimize this. In order to minimize, what we are saying is, over here it has to be a copy paste, right? The first thing has to be a copy. So how much will this give? We started with 1, right? 1 copy, 1 paste will give me how much? It will give me 2. So I can see that G1 operations, which is equal to 2 over here, is giving me 2. Now next, now what we are doing is we are copying it. We are copying this 2 and then pasting it. So after this I'll have 4. After this I will have 6. After this I will have 8, and after this I will have 10. Notice that we are just, for each of these I'm just incrementing it by this number, how much ever this number gives. So it becomes that G1 into G2 is the number after these many operations. How many operations? G1 plus G2 operations. Similarly, I can see that to reach till k, which means that G1 into G2 into G3 will become equal to k at last. Another thing to note, which is very main over here, is that if G1 can be broken down into prime factors as P and Q, then we can say that those P power P and Q, right, if it can be broken down, this G1, right, suppose this G1 was 6, it can be broken down into n equal to 6. So suppose this G1 was 6, right, 6 can be written as 3 into 2 or else 6 into 1. By this I mean that I can do these operations or these operations. Better is this operation, right, if we can break it down. In the sense, by breaking it down, what we are doing is we are neglecting, or we are what we'll call optimizing our cost to reach that number. Because if we are doubling down somewhere, right, over here after these many operations, when we are copying it, we are doubling it. Over here there is no doubling effect. That doubling effect gives me the optimization, so that I can reach in 5 operations only, I can reach till 6, something like that, right? So if it is can be broken down into P and Q, let us break it down into P and Q, right? So now our final answer will become P into Q into G2, it is a prime number, G3 is a prime number, suppose for now, equal to K. Then our answer will become P plus Q plus G2 plus G3. Now all these are prime numbers we are saying. So now I just need to find out all the prime factors and then just add it. So if there is 2 power 2 into 3 power 3 giving me that K final target, I can just say that 2 plus 2 plus 3 plus 3 plus 3, which will give me 13, will be my answer. Same thing we can see over here. While this number is greater than 1, what I am checking, I have a current at 2. In the sense, I am not dividing it by 1, but I am dividing it by 2. From 2 I am starting the prime factor. I am checking, is 2 a prime factor for that n? So n modulo 2, is it equal to 0? If it is, I'll just n by 2 it till it is being divisible by 2, I will take out all the prime factors which are 2, so I'll get 2 power k. And every time I'm doing this, I'm also adding 2 to my answer. Answer plus equal to 2 I'm doing every time over here. Next, as soon as I'm done with 2, I know that there are no more prime factors which are 2 for this n. I will go and check for 3. How many and till where I will go? Ideally I will go till root n, right? Because after that it just like n into suppose root n, because if k into k was this, right? So then root n would become our k. So this k is this. So order of k would become order of root n for us. Now if I can say that I will go to 3 and I will again check for the same thing, and modulo 3 equal to 0. If it is equal to 0, I'll just do n by 3 and then add it to the answer, and again n by 3 till it is being divisible. Supposedly for all the prime factors till root n I will go. I'm doing it ideally till root n only will go, because the algorithm is like that and math is supporting it. And we'll be adding it to the answer, and then at last we'll be returning the answer. So this is just order of n, whereas the other one was order of n square. So this is a very good problem. I like this one. Like, it took some time to just understand this bit of it, the math of it, but it was totally worth it.